Hi everyone, welcome back to class Carbon Capture Storage. In today's class, we are going to review the basic fluid mechanical property of the CO2. First, we are going to review the basic properties such as density and viscosity with a changing pressure and temperature. And then we will move on to how to calculate the pressure losses in the pipeline transportation in the CO2. After we finish the pipeline flow in the CO2, we will move on how the CO2 will flow in the circumstance of the porous media. In the left figure, as a first slide, we have a phase diagram of the CO2. The phase diagram indicates the different phase state of the given fluid. This is specifically for the CO2. And in the y-axis of the figure is shown as a pressure, and the x-axis indicates the temperature. And the temperature is given in the unit of the Kelvin, which is the absolute temperature unit, and the y-axis are given in the megapascal. Please note that 1 megapascal is about 10 atmospheric pressure, and the atmospheric pressure is about 0.1 megapascal. And in this phase diagram, we have two crucial points. First point is triple point, and the second point is a critical point. Triple point is temperature and pressure where the CO2 can exist in any state, like solid, liquid, or gas. And after this, once the CO2 reaches to the certain pressure and the temperature, it reaches to the critical state. And once we have a higher temperature and pressure than this critical point, then we will have a supercritical regions where the CO2 have a characteristic of both liquid and then gas. And this phase diagram is split by the three different lines. And the first line goes like this, and the second line coming like from the triple point to the end here, and then the last line is between the triple point and the critical point. And this line indicates the boundary of the two different phases, such as this line indicates the boundary between the solid and liquid, and this line boundary for solid and the gas, and then this one is for the liquid and gas. Triple point is about minus 56.4 degrees Celsius, and its pressure is about 5 atmospheric pressure. And the critical point here, it has about 31.1 degrees Celsius, and its pressure is about 0.38 megapascal. These three different lines have a different name. For example, this line that split the boundary between the solid and gas, it's called a sublimation curve. And this line is named as melting curve. And this line, finally, is called vaporization curve. And the reason why it's called vaporization curve is because from the liquid, after this vaporization liquid curve, the liquid state CO2 will be vaporized into the gas. Likewise, this line from the solid CO2, it will melt it to the liquid state. And between the solid and gas boundary, it simply convert to the gas without having the liquid, and that's why it's called the sublimation curve. If you think about dry ice, because the dry ice are existing in the atmospheric pressure, which is about 0.1 megapascal. So in the room temperature and then and also in the room pressure, the solid state CO2 never turn into the liquid when it turn into the gas, and that's why the dry ice is called the dry ice, because it didn't create any liquid, and that's because the pressure, the atmospheric pressure is lower than the triple point that is given here. Typically, when we transport the CO2 in the pipeline, their pressure and the temperature ranges are around. So temperature should be between 15 and 13 degrees Celsius, whereas its pressure is about 10 to 15 megapascal, and in this state, the CO2 will remain as the dense phase liquid. And once we inject the CO2 into the subsurface, then because the temperature of the subsurface is much higher than the surface, and at the same time, the deeper they go down, the more hydraulic pressure will be applied, and that's why we have a higher pressure and then higher temperature. And that makes the CO2 turn into the supercritical state where it has both characteristics of the liquid and the gas. It will had a density somewhere between the liquid and the gas, and at the same time it had a viscosity between these two. From the previous phase diagram, which we have on the top, we select the subset of the region and characterize the CO2's density and the viscosity in the lower two figure. So the region in the left and the right figure is corresponding to this region. And the x-axis of this plot are given in the temperature, and its unit is degree Celsius. And the y-axis on the left, we have a density. On the right, we have a viscosity, which is the millipascal second. Before I describe these two figures, I wish to make one quick point. So the typical SI unit for the viscosity is Pascal second. But however, most of the fluid had a quite small viscosity if we want to describe in the Pascal second. And that's why we came up with a poise, which is a different another viscosity unit. So basically, 0.1 Pascal second is equal to 1 poise. And also, if we said it's a centipoise, the centipoise will be equal to 0.001 Pascal second. And this is equal to 1 millipascal second. So we often describe the fluid's viscosity using the centipoise, which are given here, but that's identical to the millipascal second, and that's why the viscosity in the current form is given in the millipascal second. And as a reference, water in the room temperature, it's about 1 centipoise viscosity. So anything below than 1, that means it's less viscous than the water, and anything more than 1, that means 1 centipoise, that means it's thicker than the water as a fluid. So okay, I'm gonna remove this note really quick. So from here, so we have a density changes, and different line indicate the different pressures. For example, the last line is the case when the pressure is 70 megapascal, and then this line is for when the pressure is 9 megapascal, and this one is 6 megapascal, and so on. And from this dashed line, we have split of 4 different regions. So anything on the right of this dashed line, that means the CO2 is under the supercritical state. And here we have a two-phase region where anything in between these two indicate the CO2 can exist either in the liquid or the gas. So they are coexisting, and that's why the density is somewhere between these two values. And this part is in the liquid, and this part in the gas. And of course, in the gas state, it's much less dense than the liquid or other case. And this point on the top of the crest of this two-phase region, this is the case when the critical point we have. And this critical point are shown in here. So they are the same critical point. And this dashed line is same as this dashed line, which you can see from the top. So generally, the more pressure, the higher density. But when it comes to the phase changes, then we have more dramatic changes. And also, within the gas, the density only changes somewhere between, in case of the 6 megapascal, it's between the 200 kilogram per cubic meter to maybe 100 cubic meter per meter. And then if it's liquid, it only vary between 1,100 to maybe 1,000 or less. But in case of the supercritical, even with the same pressure or constant pressure, with a different temperature, the density of the CO2 had a more dramatic changes. And same thing happened in the viscosity as well. Of course, we had a more variability in the liquid state, but it's as large as or the smaller than the supercritical changes. So in the supercritical region, we have a more steep slopes of the viscosity change, whereas the liquid it has very small. And of course, in the gas state, their viscosity is negligible and it's pretty much constant. So that's why it looks pretty flat shape. So and these two figures are from these two papers. And we can actually have several experiments to get the density and the viscosity relationship with temperature and the pressure. And that's what we have in the next slide. In this paper, the author visualized the density changes of the CO2 with a changing pressure and the temperature. And as it's a two bivariate response, so we can only visualize in this 3D visualization. So first of all, the density, it's a function of the pressure and the temperature. And as we seen in the previous slide as well, it has more dramatic changes in the supercritical region. And I assume the entire region that are shown here, they are belong to the supercritical state. As an example, if the temperature decreased from the 47 Celsius to 37 Celsius, then the density will simply doubled. And I guess that state is somewhere around, so because 9 megapascal is about 90 bar, so it's somewhere around here. So when the pressure temperature decreases is just a little bit, then it has very high and steep density changes. We are gonna work on this demo in the Python. And in the paper, in the very same paper, they provided this correlation relationship between the density and the temperature and pressure. So that basically the rho, which is the density, is a function of alpha plus alpha times temperature plus gamma times temperature square and plus setup times temperature to the 3. And each coefficient is actually given as a here, and each variable is also a function of the pressures. So basically, if we combine these two, then we will have a third order quadratic approximation of the density with respect to temperature and the pressure. And then we have this A1, like a capital A1 to capital D4 coefficient. And these coefficients are constant and given on the right table. If the density is between the 25 bar to 100 bar, then we have to use these coefficient, and it's exceeding 100 bar, then we have to use this. 1 bar is equal to 10 to the 5 Pascal. So, and also 1 megapascal is actually 10 to the 6 Pascal. That means 1 megapascal is equal to 10 bar. And as the reference, 1 atmospheric pressure is around 101325 Pascal. And it's similar to just 1 bar. So that's why we use the 1 ATM and the 1 bar interchangeably. And this is also similar to 0.1 megapascal. So because we've been reviewing pressure in the megapascal in the phase diagram. Now we are using the bar, so that's why I'm making this brief point that I wish to share. So, and in this particular formula, we have to follow this note, which is temperature should be in the Kelvin and the pressure should be in the bar. That way, we will have density which is in the kilogram per cubic meter. And this is a comparison between the experimental data set and then the correlation that we've just seen. So all the lines are the result from the previous equation, and each color indicates a different pressure condition. And the x-axis, again, it's a temperature. And of course, this green and then red, I assume these two are under the gas state, and it has pretty small misfit between the experimental data set and their corresponding correlation line. And this misfit somehow increased in the intermediate case, but overall their misfit is negligible or within the acceptable range of the error, and that's why we are going to use this equation in the further application. And then this figure again from the same paper as we've seen earlier. In the same manner, the viscosity is also a function of the temperature and pressure. And in this paper, which is the different paper, the authors visualized the viscosity changes of the CO2 with the varying pressure and the temperature. And depending on the author, they may use different unit, but we know how to convert the megapascal to the bar or the bar to megapascal. So I hope you don't get confused. And the viscosity, it's given in the centipoise. And again, one centipoise is the viscosity of the water. So in the supercritical state of the CO2, in its maximum viscosity, it's only maybe 16% of the water's viscosity. And in a much lighter case, even in the supercritical state, it's around here, then its viscosity is only maybe 2% of the water. So it's really inviscous comparing to the water. And again, it has very huge changes, maybe probably from here to here in the supercritical region. And because the maximum of the supercritical CO2's viscosity is 0.16, and then minimum is about 0.02. So viscosity has a potential to increase by the factor of 8, so it increased by the 8 times in the alternation in the pressure and the temperature. So from here to here, it increased by 8 times. And then this visualization is given within 310 to 900 Kelvin, and its corresponding pressure is between 7.5 megapascal to 101.4 megapascal. So this is our we have for today's slides. And from now on, we are going to review the papers, and then we can demo. We will demo how to use the correlation in the Python and Jupyter Notebook so that we can use it in the future application. For now, I will stop here, and I will move on to the Jupyter Notebook demonstration. Thank you.